All right, question 2. A tractor of mass 5.0. Yeah, let's just start um, by bringing out our parameters. Okay, so let me divide this into 2. Okay, so the mass of the tractor, let me write mass of the tractor equal 5.0 times 10 raised to power 3 kilogram. Okay, is used to tow a car of mass 2.5 times 10 raised to power 3 kilogram. Okay, so let me see. Let me just write mass of the car. I'll use MC. I'll use MT for mass of the tractor equal 2.5 times 10 raised to power 3 kilogram. Okay, the tractor moves with a speed of, it means that the speed associated with the tractor, that's before collision. I'll use UT equal, the speed is 3.0 meter per second. Just before turn the rope becomes taut. Okay, so we're asked to calculate the speed of the tractor. Immediately the rope becomes taut. Okay, so it means that our car is actually at rest. So it means that the initial velocity of the car is actually 0 meter per second. Okay, so we are asked to find for the final velocity. All right, so it's just like what we solved initially. So I'm going to just go straight. That is momentum before movement equal momentum after movement. So I'm just going to write the formula like the first example we solved. MT UT plus MC UC equal MT plus MC, and then the final velocity MC TC, put question mark TC. Okay, so I'm going to just substitute the value. That becomes 5.0 times 10 raised to power 3 times 3 plus 2.5 times 10 raised to power 3 times 0 equal, I should have not divided this book, 5.0 times 10 raised to power 3 plus 2.5 times 10 raised to power 3 times VTC. Okay, so the solution to this 3 times this actually will give me 15 times 10 raised to power 3. This automatically is 0. 5.0 plus 2.5 that will give me 7.5 times 10 raised to power 3 VTC. So VTC equal 15 times 10 raised to power 3 over 7.5 times 10 to the power of 3. This should give me 2 meters per second. Okay, so this actually the final velocity after collision. Okay, question 2 says we should calculate the loss in kinetic energy of the system just after the car has started moving. So to calculate the loss in kinetic energy, the formula we'll be using will actually be lost in kinetic energy equal the final kinetic energy minus the initial kinetic energy. So let's talk about the initial kinetic energy. That is the energy before collision, initial kinetic. Now let's let's save time. We already know that there are two masses and then two initial velocity. Which one of them is actually zero? Because the car was at rest. So automatically I'm not going to be introducing it into the topic and into the formula. Or better still, let me just introduce it. That is mt ut square plus half mc uc square. Automatically we know this is zero already because u here is actually zero. But for questions that the two bodies are already moving together and there is no need to cancel out, so it means that there was an initial velocity. So this is now the initial velocity for the truck, and then let's dive into the solution. So it's 1/2 times the mass is 5.0 times 10 to the power of 3 times 3.0 square. So punching this in our calculator, this will give us 2.25 times 10 to the power of 4 joules. All right, let's find the final kinetic energy. Now, this is not difficult at all. Looking at the momentum here, all we just need is to introduce half and then square the velocity. That will just give us the energy. So the final kinetic energy of 1/2 mt plus mc vtc square. Okay, so if we are having this, we does right 1/2 5.0 times 10 to the power of 3 plus 2.5 times 10 to the power of 3 times the final velocity we got was actually 2 square. So this will give us 1/2 let's see, 7.5 times 10 to the power of 3 times 4, 2 in itself, 1, 2, 2, and then multiplying it with this will actually give me let's see, 15 times 10 to the power of 3 joules, or 1.5 times 10 to the power of 4 joule. Now that's not the final answer. We've said that the loss in kinetic energy is equal to the final kinetic energy minus the initial kinetic energy. If you look at this is actually an inelastic collision. Can you see that the kinetic energy after collision now is now less than the kinetic energy before collision? Okay, so actually that justifies what we discussed when we're talking about inelastic collision and elastic collision. So this is a perfect example of inelastic collision. So now the lost in kinetic energy, we said the final is 1.5 times 10 to the power of 4 joule minus 2.25 times 10 to the power of 4 joule. So the answer to this, punching our calculator, this will give us 7,500. That's negative. It's going to be negative. So the negative sign there is actually trying to tell us that there is lost in the kinetic energy. All right, let's solve the last question. Let's say the impulse in the rope when it jacks the car into motion. Now, what is impulse? Impulse, from what we discussed, now this is not joules. We use this to represent our impulse is equal to the summation of force times change in T, and we actually said is also change in momentum, that is final momentum minus the initial momentum. So what's the final momentum? The final momentum is this, the initial momentum is this. So that's I'm going to write the formula: mt plus mc vtc minus mtut plus mcuc. All right, so simplifying this, let me see, 5.0 times 10 to the power of 3 plus 2.5 times 10 to the power of 3 multiplied by 2 minus 5 times 10 raised to the power of 3 times, where is it? 3.0 plus what's the mass of the car? 2.5 times 10 to the power of 3 times 0. Okay, so this is 7.5 times 10 to the power of 3 multiplied by 2 minus 15 times 10 raised to the power of 3. Okay, so this, let's just say 15. Where am I? No, it's about 1.5. So 2 times 7.5 give me 1.50 times 10 to the power of 3 minus 1.5 times 10 raised to the power of 3. So the answer is actually equals to 0 Newton per second. So this is the impulse of the system.